Not sure what happened, but continuing where we left off. So we're going to write our ions. We have Pb, 2 plus is lead 2. Sulfide is S2 minus. So when we do our crisscross, we get Pb2S2. It simplifies. So we have just PBS, Public Broadcasting System. Okay. Last one, NiBr2. What do we call this thing? So again, starting with your training wheels, writing what you can of the name first. We know it's some nickel bromide, we don't know which nickel. And then doing your reverse crisscross with room for a positive and negative ion. That gets us a 2 and a 1. Does bromine as a halogen have a 1 minus charge? Yeah. So that is not simplified at all. That is nickel 2 bromide. Okay. Did you feel at the end of the quiz like you knew what you had gotten wrong and you knew why? Okay. Now, how many of you used a piece of paper when you were taking this online quiz? Okay. You should have all been using a piece of paper. You're not good enough to do these in your head yet. You're not. Don't try it. If you got 100% on the quiz and you didn't use a piece of paper, then knock yourself out. You're good enough. Go ahead. Take off your training wheels. Fly! Fly! But if you're not scoring well, you need to have a blank sheet of paper and your ion Bible in front of you to do these. I can do most of them in my head, but sometimes I'll jot something down because you don't have a lot of experience with doing this yet. Now, I'll share the words of wisdom from returning students with you because I just said this to the other class this morning. So today on the agenda we are going to add compounds involving polyatomic ions. So we've done binary ionic compounds, then we've done ionic compounds using transition ions that form more than one cation where we have to use stock system. And now we're going to add to that ionic compounds made of polyatomic ions. So it's another level of complication. You will have a FIP quiz on those tomorrow. And then we'll add our fourth kind of naming. Monday you will have mixed review practice on all 4 of them mixed together. And then we will start quizzing on those. So, I just said to the other class today, I said, look, if you are going on to a college chemistry class, they are not going to hold your hand and spend 4 days on naming. If any time is spent on chemical compound naming, it might be a day early in the first year, and that will cover all forms of naming. It will be assumed that you know all of your polyatomic ions. It will be assumed that when somebody says, oh yeah, magnesium nitrate, you can visualize the formula and write it down from what they said. That you're not going through a process to figure out what that is. Whoa! That's where you need to be at if you're going on to college chemistry. I wasn't there when I went into college chemistry, and it puts you behind the 8 ball and everything else. Because as they're saying, sodium sulfate, you can't visualize what that is. You can't visualize a formula in your head. You can't record a formula. And that means you can't figure out how that's going to interact with something else in a reaction. And that's not the point of what they're saying. The point of what they're saying is like the activation energy required to get the reaction between magnesium sulfate and sodium nitrate going, plus the energy of the products. If you don't know immediately what those compounds are, you're 5 steps behind and you won't catch up. So, we're spending a lot of time on this because it's really foundational. I mean, this is heavy-duty ladder stuff. And I don't know if anybody actually looked at PBWorks. I put the learning goals for you for the week on PBWorks, and then I forgot to copy them to the paper version in here. But the big goal for this week is you can name any of these 3 kinds of compounds, and the 4th one is on there saying, it's a sneak preview for next week. But, that you'll master these 4 kinds of naming: binary ionic, transition metal stock system, polyatomic, ionic, and molecular. So that's what you got to do in the next couple days. Okay, with that, let's go on to the polyatomics, shall we? So up to now, we have been talking about monatomic ions, made up of how many atoms? 1. Now we've expanded and we're talking about polyatomic ions. Poly means more than one. Yeah. Yeah, so poly can mean 2 or 3 or 5. Polyatomic ions are where you've got a group of atoms that have bonded covalently. They're sharing electrons, and then as a group, they give up or gain electrons. You have drawn these in Lewis structures. Anybody remember our old friend? Let me get all of the electrons in there. Remember what that was called? No, you don't, because you haven't had it yet. Sorry. It's SO4 2-. It's the sulfate ion. We'll get to names a little bit. Those sulfurs and oxygens are sharing electrons. They're covalently bonded. You can't break them up. But as a group, they've gained 2 extra electrons. So this whole thing behaves as one chunk. It moves as one chunk. It does not split up for the most part. When we start running chemical reactions in the next chapter that have compounds with polyatomic ions in it, you will find that there are often times where the ion just switches dance partners. The ion doesn't break up. Sometimes it does, but very often that ion actually stays together through a chemical reaction, and you can trace it. So that is a polyatomic ion. So if you look at your ion Bible, the third little table down says common polyatomic ions. There are other polyatomic ions. Okay, these are not the only ones, but these are the ones that are most commonly seen and most commonly used. They're ordered here by charge. So positive charges are all on the top, negative charges are on the bottom. The first column is 1 positive, 1 negative, second is 2, third is 3. You get the picture. How many polyatomic cations do you see? So the 2 polyatomic cations we see are ammonium, which we use all the time. And you drew this, I think you can, yeah, you constructed this also in the molecular geometry lab. And that's ammonium. It's 1 nitrogen sharing with 4 hydrogen. And it's essentially the nitrogen lost an electron in order to bond to a hydrogen, and it's now got an extra proton there. And down an electron. This is the one that we use all the time. The other polyatomic cation is dimercury, the Hg2 We don't use that very often. It does pop up, but it's one that we use less frequently. But those are the only 2 that have a positive charge, which brings us to the bulk of what these things are. The bulk of them are what we call oxy-anions. So oxy meaning they are oxygen containing, and ions meaning they are negative. They have negative charge. So most of these things are oxy-anions. And there are a bunch of them that are formed from the same things. So there's an example here. There are 4 different oxy-anions that contain chlorine and oxygen. Only 3 of them are found on your common polyatomic ions. So let's talk a little bit about naming. If you would be so kind as to look at that chart, look at the very first column and the negatively charged, the anions, find chlorate and chlorite. Okay. Now keep going down that chart and find nitrate and nitrite. And look over to the second column, the 2-, and find sulfate and sulfite. Oy. Remember when I said that you were going to have to keep track of endings really carefully and pay attention to IDE, ITE, ATE? The time is now. This is it. In terms of naming conventions, this is something that you do not waste a brain cell memorizing this, but I'm going to explain how this works to you. Whatever is the most common of the particular anion made with the particular chemicals, the particular elements. The most common one gets the ATE ending. So, of the nitrogen-containing oxyanions, which one is more common? Nitrate or nitrite? Nitrate. It's got the ATE ending. Whatever has got one less oxygen than the most common gets the ITE ending. So ITE always has one less oxygen than ATE. With sulfate and sulfite, sulfate's more common, sulfite has one less oxygen. There is no rule, like the 8 doesn't go with 3 oxygens or 4 oxygens, the 8 doesn't go with 2 or 3, it's just all about what's most common, okay? That said, don't bother wasting a brain cell to memorize that, because you're going to use this chart every single day for the rest of the year in here. You're going to look those things up 468 times a piece, and by that time, the ones that we use a lot, you'll have memorized. You won't need to memorize nitrate and nitrite. You'll do it just by using them repeatedly. You know, my goal for you, and especially those of you who are seniors who are going to go take college chemistry, if you can do it earlier in your college career than later, while these are a little bit fresher in your head. I mean, even a 1-year gap doesn't kill you. But man, if you can come straight out of using this a lot and go straight into a college chem, you're pretty well prepared. So there are even more permutations than just the most common and the most common minus 1. If you have one less, if you have 2 less than the most common, you are a hypoite. And if you have 1 more oxygen than the most common, you're a per 8. Like I said, don't try to memorize it. Don't worry too much about it. I want you to understand that that's where these names don't come out of thin air. There is actually a system involved. And at that, you can probably just leave it alone. Okay, so shall we jump into making compounds with polyatomic ions? Let's start off with going from seeing a formula to naming it, because I think that's the easier way to do it, and we can expose some stumbling blocks. Okay, what is this stuff? Now, prior to coming in and talking about compounds and polyatomic ions and stuff, a lot of you would have said something like sodium nitrogen trioxide. That's a response I get on like pre-SLO testing, you know, because you want to name everything in there. The key to recognizing compounds that have polyatomic ions in it is just to recognize the chunks, you know, to look at that and know, oh, wait a minute, this part here is a polyatomic ion. That's a separate thing. And from there, it's very easy, because just like with binary ionic compounds, all you're doing to create a name is naming the ions. So the first part is called sodium. And NO3 is which ion? Look on your chart. This is sodium nitrate. That's it. That's the name of that compound. Wonderful. Okay. Let's do a couple more. Let's make them a little bit more interesting. So here's a good one. Okay, we got CaCO3. First piece is to identify which is part of a polyatomic ion. Obviously, that CO3 is a polyatomic ion. So, what's the name of the first ion here? Calcium. And what's that second ion called? Carbonate. You have probably all seen and probably all handled calcium carbonate. It's a major component of the shells of aquatic organisms. So if you've ever picked up a seashell or a mussel shell in a creek or in an ocean or Lake Erie, you've handled calcium carbonate. Okay, good. Now let's do, okay. Once again, the first task is to identify the chunks. And there they are. So, what's the first chunk called? Sodium, yeah. Still sodium. What's the second chunk called? Sulfite, right. Okay, good. Okay, so we've got magnesium bromate. Now let's go the other direction. Now let's start from a name and write a formula. Okay, you ready for that? You're going to have lots of practice on both of these. So if I tell you that I have oh, that one's terrible, but that's okay. Sodium acetate. I wasn't thinking. What's your first step? Write your ions. Okay. Sodium ion, Na1+. The acetate ion, this is the one that chem students always end up calling Ka-choo. You found it? And some chemistry teachers apparently get like mortally offended by that. I don't. I think it's funny. I call it Ka-choo all the time in my own head. So, Ka-choo. Gesundheit. Okay. It is CH3COO1-. It's written that way because that's actually a structural representation. There are so many carbon-containing compounds that have carbons, hydrogens, oxygens. This is the standard way to write the acetate ion because it gives a hint about its structure. So we just write it as Ka-choo, and you can. It's easy to remember then. Okay. Second step is always to do your crisscross. And so 1 and 1, which means the only thing we can do to simplify is to get those 1s out of there. And that is our formula for sodium acetate. We play around with sodium acetate in here a little bit when we do solutions stuff, because it's one that's easy to do a supersaturated solution of. And you can sometimes get a rapid crystallization to run, but it never works in here. We just look up the video on YouTube, because I can never make it work. Okay, so there's our first formula. You've just written a formula for a compound containing a polyatomic ion. Great. Let's keep moving. So we'll do calcium promate. Okay. Same thing. Write your ions out. So calcium forms a 2+, and you got to find chromate. Who found it so far? Okay, what is it, Alla? CrO4. What's the charge? 2-. Okay, so now we do the crisscross. Okay, so we do the crisscross. These simplify. We end up with this. Be very careful right here, because it's tempting to do what you would do in math and sort of apply that 2 across the board. We're talking about, remember, an individual structure that is a chromium bound to 4 oxygens. You know, it's its own structure, so we keep the ion part together and sort of separate from anything else. Okay. All right, let's do one that's more interesting yet. Lithium phosphate. So, write your ions. I'm going to do it up here, but I'll be quiet, and then you can just check your answers when you're ready. Okay, so we did our ions, we did our crisscross, we did our simplification, got rid of our 1. We have Li3PO4. Now let's go to the case that causes the most instances of tripping over one's own feet. Okay, I saved it for last because I wanted you to get a little bit more comfortable with this. Okay, so go ahead and write your ions, start your crisscross. Okay, so we get to here, we have this. When we get to the next step, which is simplification, there's one additional thing we need to do. To keep that chlorate ion as a distinct unit, we need to put it in parentheses, because what we're saying is there are two of these ions. You cannot, distribute the two across the compound. It's got to remain its own little distinct thing. So you have to have those parentheses if there's more than one of the polyatomic ion. Now, in years past, I had especially one student who absolutely insisted that even if there was only one of the polyatomic ion, she always enclosed it in brackets. Can you do that? Is it legal? Is it okay? It's not illegal. I mean, like, the chemistry police aren't going to come and arrest you. It looks silly to somebody who's accustomed to chemical formulas. Like, it makes me go, mm. If you do that and you go off to a college chemistry class, somebody will probably make fun of you, but you'll be big and tough by then and you won't care. If it helps you as a training wheels kind of thing, do it. Because for this student, like, she continually screwed up those subscripts if she didn't bracket it every time. So she just bracketed it every single time. And it looks kind of ridiculous, but it's okay. It's a good training wheels thing. You'll get to a point where you're so fluent with it that you don't need it anymore. So if you want to do that, if it helps you, go ahead. If you don't need to, great. But, if you want to do that for a little while, you can. Okay, practice problems on page 211, practice problems 1 and 2. The answers are right there in the book, so you can try your hand on those. I added, but I forgot to put up, numbers 24 and 25 in the review. So I'll add those to the board. I'm going to give you time to work, and that was the bell, so take your 4 minutes. When we come back, we'll look at your tests.